Moving on to section 4.4, reaction yields. So here we're going to explain the concepts of theoretical yield and limiting reactants/reagents, derive the theoretical yield for a reaction under specified conditions, and calculate the percent yield for a reaction. So in the last section, we talked about those stoichiometric amounts, those ratios, right? Of, there's 3 moles of this to 2 moles of that. And all of these amounts were called stoichiometric amounts, meaning they were perfect ratios. But are things really that perfect? No, right? We have like the classic hot dogs and buns scenario, right? Where there's 8 hot dogs in a pack, but 10 buns. You can never have the same amount. Same type of thing in chemistry. For example, let's say we're making grilled cheese and you need 1 slice of cheese and 2 slices of bread to make 1 sandwich. I know it's not enough cheese. Don't commit, you got to have like 2 slices at least. And now let's say we're being a classic math problem here and we want to make a bunch of grilled cheese sandwiches. We have 28 slices of bread and 11 slices of cheese. How many sandwiches could we make there? We could make 11 sandwiches, right? Because we need 1 slice of cheese for every 2 slices of bread. So if we have 11 slices of cheese, that would mean we would need twice as many breads, which would mean 22 slices of bread. We have that. So we could make 11 sandwiches. Now, why can't we make 14 sandwiches? Well, unless people just want to eat a couple pieces of bread with nothing in between, then we can't do it because we're out of cheese. Okay, so the cheese limits how many sandwiches we can make. So the cheese gets all used up and we get 6 slices of bread left over. So again, the number of sandwiches that we can make are limited by the number of cheese slices we have. So in this example, cheese is our limiting reactant. The limiting reactant is always entirely consumed, and then that will limit the amount of product that you can eventually make. Okay, so the bread in this case, there's excess bread, so it's called the excess reactant. You may hear me say reactant or reagent. They mean the same thing. Okay, when I was an undergrad, we said reagent. Yes, it was a long time ago. But some books say reagent, some say reactant. It doesn't matter. They mean the same thing. So then here's just a nice picture to show you how we can make these sandwiches. So now let's consider an actual chemical reaction. For instance, we have hydrogen gas reacting with chlorine gas to make hydrogen chloride. So as you can see, it's 1:1 hydrogen to chlorine gas to 2 for HCl. And let's say we have 3 moles of hydrogen and 2 moles of chlorine. So we have to figure out which one is our actual limiting reactant before we can say how much product we can make. Okay, so the one that makes the lesser amount of product is our limiting reactant. So starting with the hydrogen, we have 3 moles of it. And based off the reaction stoichiometry, we can make 2 moles of HCl for every 1 mole of hydrogen. So that tells us we can make 6 moles of HCl if hydrogen is our limiting reactant. Now, if we do the same thing for chlorine, we have 2 moles of chlorine, and it's 2 moles of HCl per 1 mole of chlorine, and we see that we can make 4 moles of HCl. So this tells us that chlorine here is our limiting reactant in this case. This may not always be the case because sometimes you might have a different starting amount. So don't think, oh, it's always chlorine that's going to limit the reaction. Okay, so again, chlorine is the limiting reactant and hydrogen is the excess reactant. And then here's just kind of a picture to show you. If we have, in this example, 6 hydrogen and 4 chlorines, okay, they're going to combine and they're going to end up making 8 HCl's and 2 leftover hydrogens. As we can kind of see that, we can see, okay, hydrogen and HCl and a Cl, hydrogen and a Cl, hydrogen Cl, hydrogen Cl, hydrogen Cl, hydrogen Cl, hydrogen Cl, hydrogen Cl. Everything has been used up. All the chlorines are used up. So now these hydrogen molecules here don't have anyone to bond to. They're in excess. Okay, so one thing I've noticed over the years is people get confused. They think the one that makes the bigger amount is the one that you want. It is not. You want the limiting reactant is the one that makes the least amount of product. That is the limiting reactant. That is the one that determines the most product you can make. On that note, if you may have just noticed, I said the limiting reactant determines the most product you can make. So let's think about those grilled cheeses for a second. And we were like, okay, well, I could make 11 grilled cheeses, two pieces of bread to 1 piece of cheese, blah, blah, blah. But in reality, sometimes maybe you like spaced out while you were cooking you had the bread on the butter and it burned. And nobody wants the burned bread, so you got to throw it away. Or you go to put it on the plate and it falls off and falls on the floor. The dog eats it. Now you've lost another one. Now you put the cheese on the bread and then you put too much butter on the bread and it got all squishy and you had to throw it away too. Okay, so we lost 3 sandwiches. So while theoretically we should have been able to make 11 sandwiches, we actually only made 8 sandwiches. Okay, so the theoretical yield is the most product you can make. So this is what the amount that you make based off the limiting reactant. Okay, so theoretically, in a perfect world where nothing goes wrong and science isn't a fickle mistress, everything's perfect, things like error don't happen. This basically is kind of what happens in like your labs, your virtual labs. That is your theoretical yield. Okay, so that oftentimes is what you have to solve for. The actual yield on an exam is what's given to you. Okay, so this will be given to you because you can't solve for an actual yield. This is what actually happens because science is fickle. Mistakes happen. Some things that are even out of your control. You may do everything perfect, but you'll never get exactly how much you should. Okay? For instance, with the grilled cheese, we actually made 8 when we theoretically could have made 11. There are actual chemical reasons. For instance, there might be some side reactions happening that compete and make some other products or use up some of your reactants. You could have an incomplete reaction, or you may not be able to recover all your product because it gets, stuck on the filter, or stuck in the beaker, or dissolves in the water. There's all kinds of different reasons. The reality is you're never going to get a perfect yield. So we calculate percent yield, and this is a way to see how close you are to that theoretical yield. To calculate percent yield, you take your actual yield, which is given to you. If you're on an exam or a quiz or something, this is given to you. Or if you're in lab, this is what you measure. What you measure at the end, your product. Okay? And you divide that by the theoretical yield, and this is what is calculated This is calculated based on limiting reagent. Whoops. I'm just going to put LR for limiting reagent. Okay. And you have to make sure that you're using the same units. It could be volume divided by volume. It could be moles divided by moles, grams divided by grams. Okay, but you have to make sure that your units are the same. So just a little forewarning on your exam. Sometimes what I'll do is I'll ask what a percent yield is, and I'll tell you about the reaction. You have to figure out sometimes the equation, and then you have to figure out the limiting reagent, and then you have to use that to figure out your percent yield. Okay, so keep that in mind. So let's look at this example. Upon reaction of 1.274 grams of copper sulfate with excess zinc metal, 0.392 grams of copper metal was obtained according to the following chemical equation. What is the percent yield? So let's analyze this before I start going through the slides to solve it. Okay, we're told 1.274 grams of copper sulfate. Okay. It actually should be copper 2 sulfate. They made a mistake there. Okay, and then we're told with excess zinc. So in this case, we don't need to solve for limiting reagent. We already know what it is. So excess zinc just means we put way more than we needed. Okay, so we know copper sulfate is our limiting reactant. Okay, and then 0.392 grams of copper metal. That is our actual yield. Okay, so we need to find our theoretical yield. So to do that, we're going to go ahead and use stoichiometry. Okay, so we start with our grams of copper sulfate. Okay, this is just like we do here, like I do with you guys, but just kind of, here we go. All right, and we need to go from grams to moles. Okay, using molar mass. Okay, we need to get rid of grams, so we need moles on top, grams on bottom. And that gets us moles of copper sulfate. And then we can use the balanced chemical equation to go from moles of copper sulfate to moles of copper. Okay, going back to the equation, it was already balanced. It's 1 to 1. And then we can go from moles of copper to grams of copper using molar mass. SR for stoichiometric ratio. Okay, and then molar mass of copper, just the metal. This is just elemental copper. So we end up getting 0.5072 grams of copper. We are not done yet, though. This is the theoretical yield. Okay, so this is how much theoretically you could make in a perfect world. But remember, we were told that we actually made 0.392 grams of copper. So our percent yield is the actual yield, 0.392, divided by 0.5072, times 100 to make it a percent, and it's a percent yield of 77.3%. Okay, so this is a great example of doing percent yield based off of your reaction data. And then this is just an example, ibuprofen. Back in the day, up until around 1990, the synthesis method of ibuprofen generally only would yield about 40%. And so synthesis and stuff never goes perfect. Like I said, even in the big chemical world. But in the 90s, actually, a better, both more economical and more environmentally friendly method was developed, with which nearly doubles the amount of ibuprofen that can be made. So ibuprofen, aka Motrin.